Greetings everyone, and welcome to Access Habitable Planet Atmospheric Circulation Podcast. My name is Mhlengi Ndlovu. I'm from the University of KwaZulu-Natal, where I've graduated in Environmental Sciences and I'm currently in pursuit of my honours degree in Biological Sciences. Before we talk about circulating atmosphere, I would like to take you a few steps back into what we've learned so far in our last exciting talk entitled Light and Air, where we've learned that light can be conceptualized as an electromagnetic wave which forms part of the electromagnetic spectrum. And we learned that air is made up of many small particles that move around rapidly, and that the interaction between light and air help explain red sunset, blue skies, and most importantly, causes the greenhouse effect. But now our model resulted in a world that was far too hot. So now let us look at what are other parameters which are at play except for light and air. This is basically an overview of what I'm going to be talking about. I'm going to talk about the single cell model, the three-cell model, seasonal shift of cells, global winds, the importance of circulating atmosphere, and I'll be concluding. Atmospheric circulation is basically referring to a large-scale motion of the atmosphere. The sun's radiation is the energy that sets the atmosphere in motion. So when the sun radiation hit the Earth's surface, there are great things that actually happens. We are having the large fraction of the solar radiation being absorbed, and the other fraction is being reflected back, and some fraction is being radiated back into space. And as such, we are ending up having a direct distribution of heat, and our planet is being kept cooler. To really understand atmospheric circulation, we have to turn into a non-rotating Earth, or we have to turn into the single cell model, where we are assumed that the Earth is non-rotating. We assume that the Earth is being highly simplified, it's being static, and it has smooth surface characteristics such as no continents. We'll also assume that the equator receives more heat from sunlight than the polar regions. As such, air moving near the land surface will be heated up, and air is being heated, it actually expands and starts to rise up. And as it rises, it actually moves away from its heat source. As we know, Earth is being heated above, but the atmosphere is being heated below. So the heat source of the atmosphere is the Earth, is the land surface. So as the air is rising up, it literally moves away from its heat source. So the air becomes cold, or loses heat and becomes cold. And as it becomes cold, it then starts to sink back into the land surface, where it becomes heated and start to rise up again. And we are basically ending up having that basic convection cell. But here, what happens is that the air will not just sink back into the atmosphere. It will move towards the polar regions, where the conditions will be much colder because of the differences in insolation. So as it reaches the polar regions here, it will start to sink because the conditions are cold. There's cold air, and cold air will want to sink and actually form the high pressure system here, and sinks, and then it will start to move back towards the equatorial regions, and we'll be ending up having that huge convection cell in the northern hemisphere and in the southern hemisphere. And it not only that, but as we know by now, winds flow from the regions of high pressure towards the regions of low pressure. As the air is sinking here, we are actually having the high pressure because of the air moving towards the location here in the North Pole. And as the air is moving away from, or as the air is rising up, it actually leaves a void space here. So we are having a low pressure. As such, wind will be flowing from north to south direction only, or from south to north only. So it will be directional, as in that they will be in a straight line. Okay. Also, the convection cell help to explain why the mountain tops are somehow colder than the mountain bottoms. For some of the planeteers who have been up the Table Mountain, they can manifest to this, or they can actually testify to this. Okay. As we are in the bottom of the Table Mountain, what actually happens is that you are near the heat surface, or you are near the heat source, which is the land surface. Okay, so as you are moving up, or as we are hiking up the Table Mountain, we are actually moving away from the land surface, which is the heat source, and the air beside you is becoming less and less warm and becoming more and more cold. And as you reach the mountain top, as you reach the top of the top of the Table Mountain, you will realize that it is very cold there, because you are now very far away from the heat source, and the air is being now cold, and as such it will be colder up there, and you will be having that convection of cold air moving from the top of the mountain towards the bottom of the mountain, and it will actually get heated at the bottom of the mountain and start to expand and rises up again, where it will reach the top of the mountain, where it will become cold again. And this is one of the things that makes South Africa a special place to study assessing sciences, because we can actually like experience these things we are talking about firsthand. And as I've mentioned before, on Earth, air flows from the regions of high pressure to the regions of low pressure, and that air is being called wind. But here the story becomes more complicated because of the Earth rotation, of the Earth's rotation. So now here we are actually allowing the Earth to rotate. The black arrow here on this diagram actually represents the direction at which the Earth is rotating. It rotates from here towards this direction. Okay, so now as you can see here, we are having the deflection of the air in the northern hemisphere towards the right, because now we are having the Coriolis effect. Now the air, or the wind, or the surface flow that was directional, that was north-south, is now not just north-south, because the earth is rotating. So now the wind that were to flow in a straight line without the effect of the Coriolis effect are now flowing, and as they flow towards the equator, they are being deflected towards the west or towards the right, and winds in the southern hemisphere are being deflected towards the left. They are not just flowing in a single straight line, or in a straight line, or in a directional way. Okay, so now to really understand this, you will have to think of a plane flying from the city that is in the North Pole, flying towards the city that is directly south of it, near the equator. Without the Coriolis effect, the plane will fly straight towards its intended path. But due to the Coriolis effect, which is due to the Earth rotation, the plane as it flies down the equator, as it flies down towards the equator, it will be deflected to the west of its intended path, unless of course there are pilots in there who will be keeping on steering it and anchoring it like towards its intended path. As if that was not complicated enough, it actually gets one more step complicated. What actually happens is that we no longer having, or we don't actually having, two huge gigantic convection cells. We are actually, we are not having two gigantic convection cells on either of the hemisphere, like having one in the northern hemisphere and having one in the southern hemisphere. What actually happens is that there are three convection cells, and The first convection cell is being known as the Hartley cell, which occurs between the equator and 30 degrees north and south of the equator. And it forms because of the differences in insolation, as the equatorial regions receives more heat. Air moving near the equator is being heated up. I've already mentioned this before. It is being heated, and as it heats, and as it being heated, it actually expands and rises. Okay. Okay. It actually expands and rises, and as it rises, it becomes cool and start to sink at 30 degrees north and south of the equator. Between 90 degrees and 60 degrees north and south of the equator, we have what we know as the polar cell. The polar cell is as a result of the differences in insolation, as the polar regions receive less heat than the equatorial regions. So we are having the high pressure cell here, so which is as a result of the air being so cold that it is more dense and start to sink. And as it sinks, it starts to move towards the tropics, where it mixes with the air that is coming from the equatorial regions, which is warm, and actually collides and forms the convection and start to rise up. So we are ending up having rising air here and sinking here at 90 degrees and rising air at 60 degrees north of the equator. It's the same thing that happens at 60 degrees south of the equator. So we are having that basic convection cell, which we know as the polar cell. Between the polar cell and the Hartley cell, we are having the ferro cell. Now, the ferro cell, unlike the Hartley and the polar cell, is not due to the differences in insolation. It is actually due to the friction, or the friction force, because the air that is sinking from the Hartley cell 30 degrees north and south of the equator will want to take the air beside it with it down, and the air that is rising at 60 degrees, that is rising from the polar cell, will want to take the air beside it with it as it rises up, and we will ending up having that basic convection cell there, and that convection cell is being known as the ferro cell. Now let us look at the seasonal shift of cells. In January, the position of cells is in the southern hemisphere because the sun is overhead at 23.5 degrees south at an imaginary line known as the Tropic of Capricorn. As such, the cells shift southward as the heat equator is in the southern hemisphere. In June is the completely reverse scenario. The sun is overhead at 23.5 degrees north of the equator at an imaginary line known as the Tropic of Cancer. So the cells shift northward as the heat equator is in the northern hemisphere. So now let us have a look at global winds. As you can see in these two diagrams, diagrams A and B, you will notice that winds seem to be traveling at a bunch of different directions. But what's very important to note, or what's very important to understand here, is that winds are blowing from the regions of high pressure to the regions of low pressure. So basically, where you have a high pressure cell, or where you have a high pressure system, rather, where you have a high pressure system, this is where the winds are going to start. And where you have the low pressure system, this is where the winds are going to be blown towards to. Okay. As you can see in the diagram on my left hand side, or diagram A rather, is that you will notice that winds blow from the North Pole towards 60 degrees north, and they blow from 30 degrees north towards 60 degrees north, and they blow from 30 degrees north toward the equator, which is 0 degrees. In the southern hemisphere, the winds are blowing from 90 degrees south towards 60 degrees south of the equator. They are also blowing 30 degrees south of the equator towards 60 degrees south of the equator, and from 30 degrees south towards 0 degrees, which is at the equator. So sorry. So you can see that there's a variety of directions winds are going to be blown towards, and they are all following the principles, or they are all following some sort of rules of the Coriolis effect, which is the deflection of fluids or any moving object towards the left in the southern hemisphere, and the deflection of fluids or any moving object in long distance towards the right in the northern hemisphere. Okay, and as such, we are having what we know as the winds, which we know as the doldrums, which are at the equatorial regions, or they are also called the intertropical convergence zone, or the ITCZ. On the poleward side of the doldrums, we have the trade winds. The trade winds are between 0 and 30 degrees north and south of the equator, and they are the predominant wind system of the tropics. On the poleward of the prevailing westerlies near 60 degrees north and south latitude lies the belt known as the polar front. Okay, so this is the subpolar low, or the polar front, which is 60 degrees north and south of the equator. And the polar front is the converging wind which results in ascending air current and consequently poor weather. And between 60 degrees and 30 degrees north and south of the equator, we have the westerlies, or the wind that are called westerlies because historically winds are named based on the direction at which they are coming from. So, to sum up global winds, at 0 and 30 degrees north and south of the equator, we are having the trade winds. At 30 degrees to 60 degrees north and south of the equator, we are having the westerlies. At 60 degrees, we are having the polar front zone. At 0 degrees or around the equator, we are having the doldrums, or the intertropical convergence zone. And this high and low pressure systems actually dictates many things in the earth. They dictate how or where our biomes are going to be located. And as we know, most of the Earth's deserts are being located around 30 degrees north and south of the equator. Think of the Sahara Desert. They are at 30 degrees north and south of the equator because there's a high pressure system, and the high pressure system comes with the dry air. Okay, and at 0 degrees or around the equator, at 0 degrees or around the equator, we are having the ITCZ. We are actually having the rising air, and we are having a lot of precipitation here because there's a lot of cloud formation. Same thing happens here at 60 degrees because we are having the low pressure, just as we are having the low pressure at the equator. So we are having a lot of precipitation. As such, around the equator, you will find most of your rainforest, and around 60 degrees north and south of the equator, you will find most of your evergreen forest. So, what is the importance of circulating atmosphere towards our habitable planet? At first, it determines the climatic conditions, it dictates our weather and seasonal traits, it also determines the geographic distribution of phenomenon on the Earth's surface, and we need to have a comprehensive understanding of the Earth's functioning. So, in conclusion, we know that there's an uneven solar heating, and that uneven solar heating drives the atmospheric circulation. And that atmospheric circulation results to a formation of a basic convection circular motion, and that the three-cell model is more robust than the single-cell model, and that the circular motion results into a pattern of global winds, and that circulation pattern gives rise to differences in rainfall in different latitudes. And as a result, we are having the formation of earth biomes like the rainforests around the equator, the evergreen forests around 60 degrees north and south of the equator, and the deserts around 30 degrees north and south of the equator. So, in our next exciting core talk entitled Circulating Atmosphere, we know that the atmosphere circulation keeps our winds, climate, and we know that our atmosphere circulation explains our winds, climate, and keeps the planet cool. Now we have a habitable planet, right? Wrong. We also need to consider the role of the ocean in climate, which is maybe more important than the atmosphere. So in our next exciting talk entitled Circulating Oceans, we will find out about the role of other fluid that influences the habitable planet. When the ocean and the atmosphere get together, they dance like all good couples do. So we will also pick up some new dance moves. Thank you for watching, and I hope you gain a lot by watching this podcast, and I'm hoping you'll be having a great day. Thank you again.